So before we can really delve into naming compounds, we have to consider a few things. One of the things we have to consider is we have to look at the, see, is this, well, first, is it for sure a pure substance? We don't want a mixture. What do I mean by pure substance? I mean that it's just helium. It's just water. It's just oxygen. It's just ethanol. That's what I mean by a pure substance. It's not a mixture of more than one thing. Air is a mixture of multiple things. You've got nitrogen, oxygen, carbon dioxide. There's other things in air, but that's a mixture. I cannot have a homogeneous nor a heterogeneous mixture for naming, because I would have to name each individual species separately and then say they're all part of the mixture, okay? So for naming, I need to first determine that it is in fact a pure mixture. Or pure substance, I apologize, a pure substance. Once I know for sure it's a pure substance, meaning it only contains one component, I need to determine, is that an element or is it a compound? What do I mean by that? What I mean is that there are some elements on our table that don't exist naturally as just one single atom of that element. There are some that exist as diatomics, and then there's a handful that exist, they prefer to exist as a polyatomic, meaning multiple atoms of the same element bound together. So once you determine it's a pure element meaning that you can find that symbol on the periodic table. And it's just got one element in it. From there, I need you to determine, is it atomic or is it molecular, or even from there, it could be polyatomic. Not a polyatomic, and I want you to be careful with that term. In this sense, I mean multiple atoms of the same thing. We will also learn polyatomics, which we use as a broad term to represent compounds that have multiple elements in them that have a charge to them. But here, when I say polyatomic, I mean, truthfully, I mean more of a polyatom type situation. And I'll talk about the cases that occurs in. If it is atomic, this means it is a single atom. So the particles are single atoms floating around. Hydrogen, if I talk about hydrogen, if I just say hydrogen, that is not atomic. Hydrogen exists as a molecule, a diatomic specifically. You're going to have to memorize which ones are diatomics and which ones can do a polyatom compound. Anything that doesn't fall into that category will be atomic. Helium. If you ever got a balloon filled up for you and it floated, like it actually floated in the air, so it wasn't just filled up with our breath, that was filled with helium. Helium is atomic. It exists as a single atom floating around. If you think about neon is a lot of those signs that light up on storefronts or restaurants at night that are really brightly colored. There are different gases that are inside of there, but oftentimes we use neon gas for those. Neon has a very red, orange, bright color to it. Neon is atomic. It is particles of single atoms floating around. So if I say I've got a container of helium gas, that means I've got little tiny heliums floating around. So each little dot here would represent one little helium atom. Molecular is particles are molecules. Molecule means more than one atom bound together. Most often, we're talking about diatomics. See here on each one of these, we have two atoms bound together. So again, most often, we're discussing diatomics. Di and then atomic. Di meaning two. There are 7 diatomics that we will talk about in another section that you will have to memorize. There are also 4 elements that like to exist with multiple atoms, more than 2 put together. You need to know those. Those are the favorite, most natural states, and you need to know those. If you memorize those, that's memorizing 11 out of the 118 or something like that elements that are on the table. I don't remember how many we're at this point. Physicists have been creating more past a certain element. If you memorize those 11, though, you know everything else is atomic, and those are not, and you'll be okay. What if we go the other direction? What if we go from pure substance to compound? Under compound, we can have molecular or ionic. So molecular compounds are the smallest representative particles that we can call molecules. These are nonmetals. Molecular compounds have covalent bonds. And as we just talked about in the previous section, covalent means a sharing of electrons. It doesn't have to be an equal sharing, but it is a sharing of electrons. Ionic is a formula unit being used to represent the smallest particle, such as sodium chloride. So we see here our example, water is a molecule. Water has an oxygen atom and 2 hydrogen atoms that are bound together. We draw it in this bent structure. It's what it's called, is bent. We draw it in the structures. That's how it actually exists in 3D space. And you guys are going to learn that later this semester. But this is water. Water is not, oxygen pulls a lot of electron density to itself, yes, but it's still sharing with hydrogen. In a sodium chloride compound, the sodium has completely given up its electron, and the chloride has completely taken that electron. So this is an opposite charged attraction holding these two things together. It's not a bond in that sense. We use a formula unit to represent the smallest particle because this is the smallest it can get and still be sodium chloride. Excuse me. So some molecular ionic properties. Molecular, again, nonmetals, covalent bonds. Molecular compounds only have weak attractive forces between uncharged molecules. We will talk about these attractive forces more in chapter 12. We talk about intermolecular forces as a whole, but they're much weaker forces holding these together because they are sharing these electrons, and it's kind of like, okay, I want some of that, but I want some of that too. Okay, we'll share. So it's a weaker attraction holding these two things together. In ionic compounds, we have that full positive and negative charge attraction. That's a lot stronger attraction. Molecular compounds generally have a low melting point and low boiling point. MP means melting point, and BP means boiling point. They tend to be low because in order to melt something or eventually boil something, I need to destroy or pull apart the molecules from the other molecules. In order to do that, I need to pull the molecules apart. In order to do that, I need to completely destroy or overcome the intermolecular forces holding the molecules together. So if it doesn't have very strong forces holding it together, it's a lot easier, it takes a lot less energy to pull them apart, hence a lower melting point and a lower boiling point. Molecular compounds can exist as solids, liquids, or gases at room temperature. There are a lot of nonmetals are gases. A lot of them are gases at room temperature. There are definitely solids at room temperature. The lower we get on the table and we're still in the nonmetals, they're going to be solids. The only liquid nonmetal at room temperature is bromine. And bromine is actually diatomic, so it exists as Br2. This is a liquid at room temperature. There's only 2 elements on the entire table that are liquids at room temperature. Bromine is one, mercury, which is a metal, is the other one. Molecular properties, non-conductors of electricity. Nonmetals do not conduct electricity. They want the electrons, they don't really want them passing by them. They're not going to conduct electricity. Instead, they're insulators. And they're usually non-electrolytes. We will talk more about what an electrolyte and non-electrolytes are in chapter 5, but most often molecules are non-electrolytes. And this goes back to the non-conductors of electricity. Electrolytes are able to transfer electrons through solution for a very specific reason. Most likely molecules cannot do this. Or most often non-electrolytes cannot do this. We see here a nice structure of a molecular compound. They're just kind of floating around out there. Water, glucose, ethanol, acetone, all of these things are molecules or molecular compounds. Ionic compounds, on the other hand, are hard, brittle, and high melting crystalline solids. Notice the word solid. The only metal that is not a solid at room temperature is mercury. It is a liquid. It's a very heavy liquid, very dense liquid. Ionic, though, tend to be very hard. We're holding together particles that have oppositely charged attractions. They really like each other. They're going to be very hard. Think about metals. Think about salt. In order to break up, I know we have salt in tiny little pieces, but if we tried to actually grind that up into a powder, it actually takes some effort. They are brittle. They do break apart. They tend to be high melting. High melting because I need to overcome these full attractions and pull these guys apart. It's going to take more energy to do that. Hence, it's going to have a higher melting point. They are non-conductors in their solid state, but conductors when molten. Molten means melted. So in their solid state, they're not going to do anything. They're just going to sit there. If I take a giant cube of salt, of sodium chloride, and just put electrodes on it and see if it's going to conduct electricity, it's going to stare at me. If I dissolve salt in water and let it become ions, it will conduct. If I can melt something, if I can melt one of these ionic compounds, it will also transfer electrons. And their electrolytes mean they separate into ions in aqueous solution. And that is why, what I was just talking about, if I put sodium chloride in water, AQ means aqueous. Aqueous means dissolved in water. It will break itself apart into sodium ions and chloride ions, which will then also help transfer electrons through the solution and act as an electrolyte. So different type of chemical formulas you're going to see throughout class. We've got where we've just write CH4. This here is going to be the most common form you are going to see in this class. That's how we're going to write most formulas. We're just going to write out what we have. This is called your molecular formula, and it shows how many of each atom are in each molecule. We can also, again, call this a formula unit if it is an ionic compound. Beyond just teaching you guys that these two things are different, we don't really specify beyond that throughout the rest of the semester. We just kind of write them as the formula. So you need to recognize that ionic compounds, when I write them this way, are not actual molecules, but rather a formula unit, but we don't really harp upon it throughout the semester. We've got your structural formula. This shows you how the atoms are actually attached to each other in that molecule or that compound. So this you're going to have for molecules. Ionic compounds aren't going to do this because they don't actually create that situation. They create these 3D structures of oppositely charged attraction like we've seen in the like this for sodium chloride. Okay? So this structural formula you're going to see for molecules. We're going to learn how to do that in chapter 10. You're going to learn how to put these together and see how they're connected. The ball and stick model and space filling model are very important, but used a little bit less in Gen Chem 1. That doesn't mean you won't see it. You will see it, but they're not as commonly used in our class. We're going to use, again, this the most throughout this semester. We're going to learn how to do this and this near the end of the semester, or, well, closer to the last third of the class at least. We're going to learn it there. The advantage to the structural formula is to see how the atoms are actually connected. The advantage to the ball and stick model is we can see how the compound looks in 3D space. And space filling is used, we need you to picture this in your mind, because this, and especially if you take organic next year, you really need to be able to picture this in your mind. You need to be able to see how these molecules can interact with each other. So this comes into play more in your mind than drawing, because to be honest, I can't draw a space filling model. I need a computer to draw it for me. And it's just harder to do that. It takes more time. I can't draw that. I don't know how to effectively draw that. I can draw this. I can't draw a space filling model, at least not well. But we need to be able to visualize that space filling model in your head. So again, that is for molecular compounds. For ionic compounds, we will write just that base formula. And then we were going to talk about empirical formula near the end of this chapter. And the empirical formula is what shows the simplest ratio of our ions in an ionic compound. So ionic compound is, empirical formula is defined as the lowest whole number multiple ratio. I will define that again. I will write that out. But that's how, truthfully, this, where I write NaCl here, this is truthfully called your empirical formula. So naming compounds. First, to name a compound, you must determine, is this compound ionic or molecular? Again, what do I mean by ionic or molecular? I mean, does it contain a metal or not? If it is ionic, that means it contains a metal. You need to follow through for the appropriate way to handle that if it does in fact contain a metal. Ionic compounds most often will be one metal and one nonmetal. If it's containing just two elements, we call it binary. If it's containing three or more kinds of elements, so three or more different elements, we call it a polyatomic. Now, the only exception to this rule here is that sometimes you can have two polyatomics that are oppositely charged that form a compound and act as an ionic species. Or is it molecular, meaning covalent? This contains non-metals only. This is ionic is where we have a transfer of electrons. Molecular is where we share electrons. And again, as we talked about in the previous section, truthfully, it's a spectrum. The compounds exist with ionic and covalent character most often. The different molecules will create a bond that has both character of each, but we are going to quickly just define one as one or the other so that we can name it. So there's a naming convention we're going to follow. If we see the metal nonmetal, we're going to name it as ionic. If we see all nonmetals, we're going to name it as a molecular compound. So molecular, we need to use number prefixes with molecular compounds that are binary. We'll go through all that in a different section. And again, binary just means it contains two elements only. Very important thing to remember in this section is that metals tend to lose electrons and become cations. Nonmetals want to gain electrons and become anions. If you can remember, metals are going to lose, anions are going to gain, or nonmetals are going to gain. Metals form those cations, nonmetals form those anions. It will make naming so much easier for you. So just really quick, let's go through an example to determine if the following compounds are ionic or molecular. Because the first thing you need to do is identify when you do these yourselves, are these all nonmetals or is this nonmetal metal? So PCl3, I've got phosphorus and I've got chlorine there. When I look on the table, I find phosphorus, I find chlorine, they're not too far away from each other, and I see they are both to the right of my stair step, my metalloid stair step, which means they're both nonmetals, so this will be molecular. Magnesium bromide. Magnesium is under group 2. It's an alkaline earth metal. Bromine, one of my halogens, group 17, nonmetal. So I've got a metal and a nonmetal. This is definitely ionic. KF. K stands for potassium. It's what's in bananas. You need potassium in your diet. If you don't like bananas, find it. It's in a lot of other places too. Bananas is just the first place I think of it. But potassium is a group 1 metal, alkali metal. It's being paired up here with fluorine. Fluorine is a halogen, group 17. So this will also be ionic. CS2. C stands for carbon. It is the most abundant element on the entire planet. It's in, if you add up all of the carbon-containing compounds, and put them in one pile, and then in another pile put up every single compound in the world that contains anything but carbon. The carbon pile wins. It is the most abundant element there is in this world, which is why the periodic table is based on it as well. Carbon is a non-metal. It is to the right of your stair step. Sulfur is S. Sulfur is also a nonmetal. It's under your chalcogens. It's underneath oxygen of the table. So this will be a molecular compound. SO2, we just talked about sulfur, how it's under oxygen in the table. It's a chalcogen. It is a nonmetal. And oxygen, hopefully everyone remembers that one at least, is also a nonmetal. So that will be molecular. HBr. This one's actually kind of tricky. If I am looking at HBr as a gas, hydrogen is a nonmetal, bromine is a nonmetal, bromine's a halogen, so this will act molecular. If I am talking about HBr that's dissolved in water, this is an acid, and this will act more like an ionic compound. It's going to act as a strong electrolyte. We'll talk about strong weak electrolytes more in the next chapter. For this, if I was to ask you this just right now today, you could assume that that is in fact molecular. Note that hydrogen is on the other side of the table though. When you look at the table, hydrogen's up here. That's because of the number of electrons it has. Hydrogen is in fact a non-metal gas and fits over here when we're looking at properties of the compound in that way. We put it above the group 1 metals because it does have one electron it wants to lose. Fe2O3. Fe is iron. Fe comes from its old name, ferric and ferrous, different oxidation states or charge states of iron, but iron is a metal. And oxygen, of course, we know is a nonmetal, so this will be ionic. NaCl, it is probably our most used, probably overused example of an ionic compound, but as a reminder, Na is sodium. It is group 1 alkali metal. Chlorine, Cl, in this case, actually, this is sodium ion chloride ion. We'll talk about the naming of that in another video. But chloride ion, chlorine is group 17 halogen. pH3, P, we already talked about, is phosphorus. It is to the right of our stair step, so it is a nonmetal. And hydrogen, although residing here on the table, is in fact a nonmetal. So this will also be molecular. CuCl2. Cu stands for copper. Cu, close to what you would think of for copper. Co is actually cobalt, so don't mix up copper and cobalt. Cu, copper, metal. Cl, chlorine, group 17 halogen, nonmetal. C6H6. C6H6 is known as benzene. It's a carcinogen. You'll hear about it in different compounds. People warn you like, oh, don't use benzene. We don't use it in organic lab anymore either. But C6H6 is carbon and hydrogen containing. Carbon, nonmetal, hydrogen, nonmetal. And lithium bromide. Lithium, it has an atomic number of 3. It is under your group 1 metals. It is an alkali metal. So it is, well, definitely a metal. Bromine, we've already talked about, group 17 halogen is a nonmetal. So this will also be ionic. Make sure you can quickly recognize these a lot faster than I did here, of course. Here was to kind of walk you through the thought process for each, but you should be able to look at these very, very quickly and immediately be able to tell, is this molecular or ionic? If you can do that, then you can go to the next step, which is actually naming the compound, but you have to be able to do this very fast.